Good morning, guys. Welcome to the session, and today we'll be continuing our discussion on complex analysis. And today we'll be revising the previous two topics, Taylor series and Laurents series. We'll do some problems so that you understand it better. So let us start with a problem from Taylor series. Okay, if everything is all right, let me just check. If everything is all right. Okay, so I hope everything is all right. Let's start. So let's start with this problem. Find the first few terms of the Taylor series expansion of the complex variable function. The function is given by f of z is equals to z plus 1 divided by z minus 3 times z minus 4. Okay, about z is equals to 2 and also find the region of convergence. Look, this problem you can try in two different ways. As I told you, as we have done on the last day, the expansion method, and another way you can do, someone of you was asking also, by using the Taylor series formula. So let's try to do this problem. Deep was asking this, na? Can you do it using the original Taylor series formula or not? So will you give it a try? Region of convergence means the region where this expansion will converge. If you plot this function f of z versus z, let's say y versus x graph, if you plot, what kind of graph you expect? About z equals to 2, so this is 0, let's say this is 1, this is 2, this is 3. Now as you can see, this function f of z equals to z plus 1 divided by z minus 3 times z minus 4, where it has the singularity. The singularities lie at z is equals to 3 and z is equals to 4. You know one thing, that for the Taylor series expansion, the function must be analytic, na? The function must be analytic. This is the required criteria, and the singularity point, those points are the point where the function ceases to be analytic. the function is not analytic at those points. So at z is equals to 3 and z is equals to 4, at these points the function is not analytic. So we cannot expand the function here. Z is equals to 3, z is equals to 4, these are singularities. So z about z is equals to 2, z equals to 2, what does it represent? Mod z equals to 2, if you consider, that represents a circle, है ना? So about z is equals to 2, you have to find out the expansion. So region of convergence should be mod of z minus 2 less than 1, isn't it? Region of convergence should be, if you want to expand it about z is equals to 2, the region of convergence should be z minus 2 less than 1. If it is more than 1, then it will include this 3 point. Try to understand it very carefully. This is a very interesting thing. You see, is it clear or not? This is the region of convergence, and if it asks you circle of convergence, it should be z minus 2 equals to 1. So z minus 2 equals to 1, this is the circle. Region of convergence means the inside point of this circle. Why it is region of convergence? You see, if it becomes more than z minus 2 greater than 1, if it becomes greater than 1, then the circle will be bigger. The circle would have been like this, the circle would have been like this, and that will include this z equals to 3, and that will make the series diverging. Understood? So this is the region of convergence. Is it clear or not? Look, this concept is very crucial, that is why I am giving you time here at this concept. Is it clear to everyone, this region of convergence concept? And once you decide this region of convergence, the remaining calculation is very similar. So we can expand it in the Taylor series. F of z is equals to z plus 1 divided by z minus 3 times z minus 4. So you can expand it in partial fraction by doing a by z minus 3 plus b by z minus 4, and you can easily calculate the value of a and b. The value of a will come minus 4 by z minus 3, and value of b will come 5 by z minus 4. So this one we have calculated by partial fraction method. Partial fraction method. Okay, so this is a very standard problem. We'll do the way we did on the last day, then again we'll try to do the same problem using the Taylor series formula, and you will see that both the approach will give you the same result. Fine. So here you have to do the expansion about z equals to 2. So what terms you can expect? Z minus 2. Z minus 2 terms should be expected. So minus 4 divided by z minus 3 is there, so we can write it as z minus 2 minus 1, z minus 2 minus 1, and z minus 4 you can write z minus 2 minus 2. No issue in this. So this becomes, if you take this minus 1 common, because z minus 2 is less than 1, this is the criteria. So you can take minus 1 common, so minus minus plus, So 4 times 1 minus z minus 2 inverse minus 5 by 2. If z minus 2 is less than 1, z minus 2 by 2 will also be less than 1, no issue in that. So 1 minus z minus 2 by 2 inverse. Can you write it? This one we could write because z minus 2 less than 1. So we can expand it now. In infinite series you can use binomial expansion. So this will become 4 times 1 plus x square plus x cube and so on. On the other hand, 5 by 2, 1 x is now z minus 2 by 2, z minus 2 by 2 whole square, z minus 2 by 2 whole cube and so on. Now let's gather the coefficient. Firstly constant 4 and from here minus 5 by 2. Next arrange the coefficient of z minus 2. So here it is 4, here it is minus 5 by 4, z minus 2. Now gather the coefficient of z minus 2 whole square, it is 4, and here you see 1 by 4 minus 5 by 4. So 5 by 8, 4 minus 5 by 8, z minus 2 by 2 whole square, plus in the same way it will give you 4 minus 5 by 16, z minus 2 by 2 whole cube and so on. Sorry, we have already taken care of these two, so only z minus 2 will come here also. So if you simplify a little bit more, so this will give you 3 by 2 plus 11 by 4 z minus 2 plus 27 by 8 z minus 2 whole square plus 59 by 16 z minus 2 whole cube and so on. Okay, so this is one approach we have learned on the last day. Now let's say if you want to apply the original Taylor series formula, then what you can do? Let's say alternative method, you can reach to the same answer by taking up the alternative method. Here we have taken up the binomial approximation or binomial expansion method. Another thing, you know, if you want to expand it in Taylor series about z equals to t, so expanding f of z about z is equals to 2. So you know the formula, right? F of z, you can write it as f of 2 है plus, okay, so I am writing the original formula, then you can just put z a equals to 2, f of a plus z minus a prime a plus z minus a whole square by 2 factorial f double prime a. Do you remember this formula? Z minus a whole cube by 3 factorial f triple prime a and so on. So just evaluate the values. What you need to find out? You need to find out f of 2, f prime of 2, f double prime of 2, f triple prime of 2. Do it quickly. Good morning, Thamish. You were absent on the last day? Where is Murli? Harry, Ajay, Deep. Okay, can you do it using the original Taylor series formula? Can you tell me what is the basic difference between Laurents series and Taylor series? Anyone? Good morning. What do you think? What is the basic or fundamental difference between Taylor series and Laurents series? When we expand a complex function in Taylor series and when do we expand a complex function in Laurents series? Anyone knows? You see, for Taylor series expansion, the function must be analytic. If at some point the function is not analytic, we have to exclude that. As you can see that the function is not analytic at z is equals to 3, z equals to 4. So we have to take up such a region which is entirely analytic. So this region is purely analytic, where the function is purely analytic. But in case of Laurents series, we expand about some non-analytic function. Okay na? So as you have seen in Laurents series you also will revise today. So you can expand about this point, let us say z equals to z0, but the function may not be analytic at this point. It is analytic in this annular region. We will talk about it. Let us tackle this. Look, if you calculate this f of 2, f prime of 2, it becomes difficult. So first of all, we have to simplify the given function. So f of z, which is given as z plus 1 by z minus 3 times z minus 4. So we can simplify it by using the partial fraction, and you can just easily find out the value of this thing. So this will give you minus 4 by z minus 3 plus 5 by z minus 4. This will give you the value by partial fraction method. No issue in this. Now we need to calculate f of a. So z equals to a equals to 2 here. So what is the value of f of 2? Either you put here or here, any value we put. So 2 plus 1 divided by 2 minus 3, 2 minus 4. So if you put here, let us say 2 plus 1, 2 minus 3, 2 minus 4. So original value putting is easy for this function. So this is 3 by 2. F prime of z, let us calculate the value from here. So this is 4 by z minus 3 whole square minus 5 by z minus 4 whole square, and hence a prime of 2 equals to 4 by 2 minus 3 whole square minus 5 by 2 minus 4 whole square. So what is the value? What value are you getting here? Four minus 5 by 4. 16 minus 5 by 4, 11 by 4. है ना. So f double prime of z you require. So taking derivative of this function again, minus 8 by z minus 3 cube minus minus plus 10 by z minus 4 cube. Clear? And if double prime of 2 becomes 8 minus 8 by 2 minus 3 whole cube plus 10 by 2 minus 4 whole cube, and this will give you 27 by 4. Let's calculate another term, f triple prime of z. F triple prime of z means derivative of this thing again, so 24 by z minus 3 to the power 4. Non-negative power of z, in Taylor function must be analytic. Yes, in Taylor function must be analytic. This one needs to be remembered. So this is 24 by z minus 3 to the power 4 minus 30 by z minus 4 to the power 4, है ना. So what is the value of f triple prime of 2? 24 by 2 minus 3 to the power 4 minus 30 by 2 minus 4 to the power 4. So this will give you 177 divided by 8. If you calculate, you will get this. So your Taylor series expansion will give you f of a, so f of 2, है ना, f of 2 plus z minus 2 f prime of 2 plus z minus 2 whole square by 2 factorial f double prime of 2 z minus a whole cube by 3 factorial f triple prime of 2 and so on. Now just put the values. F of 2 we have got 3 by 2 plus z minus 2 f prime of 2 is 11 by 4. So are you getting what you have obtained in the previous answer? Tell me, are you not getting the same thing you got in the previous answer? Three by 2 plus z minus 2 times 11 by 4 plus z minus 2 times whole square 27 by 8 plus z minus 2 cube divided by 59 by 16 and so on. So I think you are getting the same result. Yes. So which approach is easier? Obviously the first approach is easier, huh? So that is why we generally did the first approach on the last day. But I have also shown you that alternative method also exists. So depending on the function, if the function is like suitable for derivative, then you can use the original formula. Otherwise this formula will always work. You make it in the form of 1 minus x to the power minus 1 or 1 plus x to the power minus 1, whatever suitable, and expand. That is, I think, easier. What do you say? Which one is easier and simpler? First or second? First one, na? Yes, I also think so. Let me give you a simple problem, then we'll go for Laurents theorem. See, if you can do this problem, expand the function sin z by z minus pi about z is equals to pi. Look, this particular topic, complex analysis, is a must topic. One question will definitely be there in your examination. Okay, I think there is no exception of this one. So that is why we are doing it with a lot of problems, and I hope after attending the session you will be able to answer questions. So it may take a couple of sessions, more couple of sessions. So your duty will be to revise whatever we do on a particular day. You should be revising it once before attending the next class, then it will be effective. If you are learning it for the first time, then it may appear little difficult, but if you revise it 1 or 2 times, then it will appear to be very easy. Complex is very easy topic, okay, provided you revise. So how will you do this problem? Expand the function sin z by z minus pi about z equals to pi. Look, as I told you, about z equals to pi, so what will be the terms in the expansion? It will be z minus pi, right? It will come in terms of z minus pi. So if you put z minus pi equals to t, so it will come in the form of t square, t cube, or whatever terms survives, that will come, and at the end we can just replace t with z minus pi. Okay, so what you get, because you see sin z we have, so we can write it sin t z is equals to pi plus t. So sin pi plus t divided by t. Now sin pi plus t is what? Minus sin t. So this is the reason we took z minus pi is equals to t. We have assumed some variable because we have sin in the numerator, and if you put z equals to pi plus t, it becomes minus sin t. Now the next process is quite straightforward. Minus 1 upon t sin t, you know the expansion of sin t, t minus t cube by 3 factorial plus t to the power 5 by 5 factorial minus t to the power 7 by 7 factorial, and so on. So this is basically giving you 1 minus plus t, so t square by 3 factorial minus t to the power 4 by 5 factorial plus t to the power 6 by 7 factorial minus dot dot dot. So this can be written as minus 1 plus z minus pi whole square. The rule is simple: what you have taken you have to give back. So we have taken z minus pi is equals to t, so at the end we are just returning it back. Fine, this is the required expansion. Was it difficult, guys? So this is quite simple. Okay, so I think you have understood Taylor series now very well. Now let us talk about Laurents series. In Laurents series, we have already talked about it on the last day. There is a little correction in the Laurents series expansion. Okay, so do the correction. I am giving you the new version. You just note them down. Everything will remain same. Just some integration value. The contour may be on the last day given to be incorrect. So just rectify it, and let me just give you that. Okay, so note down this Laurents theorem, then we will solve some problem. If we required to expand f of z, just wherever you wrote Laurents theorem, just cut it and write this one. If we require to expand f of z about a point where f of z is not analytic, then it is expanded by Laurents series and not by Taylor series. So Taylor series expansion is done where the function is analytic, and as you can see in this point, in this figure, the point z equals to a, this is, let's say, not analytic for the function, but this annular region is the region where the function is analytic. So for this kind of case, we will use Laurents theorem or Laurents series expansion. If fz is analytic on C1, means this trajectory, and C2, this trajectory, and the annular region are bounded by the two concentric circles C1 and C2, this annular region it is talking about, provided R2 is less than R1, R2 is the inner radius, R1 is the outer radius, with center at A, then for all z in R, it may be here, anywhere, f of z is equals to this a0, a1, z minus a, a2, z minus a whole square. So this is the formula we gave you on the last day. This is your summation n is equals to 0 to infinity n z minus a whole to the power n, and plus n is equals to 1 to infinity bn by z minus a whole to the power n. Okay, where this n is equals to 1 by 2 pi I integration over the outer circle. On the last day I think we told integration on the, okay, this formula we gave it correct. Okay, whatever it is, just note down. I think same formula we gave. F of w by w minus a to the power n plus 1 dw. So previously we wrote f of z, so it can be written as f of z because z is a variable. Na? So f of w by w minus a whole to the power n plus 1 dw, and bn is 1 by 2 pi I integration over the inner circle C2, fw by w minus a to the power minus n plus 1, there is no bracket here, minus n plus 1 dw. So just note it down, this bn has special importance. Later we will see that by putting n equals to 1 we get something called residue, you know. So that is why this is very important. For bn we have to consider this inner circle C2, for an the outer circle C1. Just note it down, this one we took from H.K. Das. Let me know once you are done, then we will go for some very good problem on this. Then you will understand the difference between Laurents theorem and Taylor's theorem. Done? Note it down very carefully. Here it is n plus 1, here it is minus n plus 1. Okay, chalo, I had if you have done it, then what about Deep, Harani, Tamiz, Murli? You guys are done? Let's solve this. Expand f of z equals to 1 by z plus 1 into z plus 3 in Laurents is valid for. Okay, so we are considering 4 regions, same function for 4 different conditions, and I think after this you will have no issue with this expansion problem. You can do any problem given to you. So let's start with the first one, 1 less than mod z less than 3. For this condition, try to expand this. So first of all, let us try to graphically see this region. Yeah? So we have to expand f of z is equals to 1 upon z plus 1 z plus 3 in this region, 1 less than mod z less than 3. So we can write it as, okay, you see, half times 1 upon z plus 1 minus 1 upon z plus 3. You see, if you do 1 upon z plus 1 on minus 1 upon z upon 3, you get z plus 3 minus z minus 1. So 2 by this thing. So that is a half is multiplied. Okay. So this is the general thing we will apply for every case. Now let us try to visualize this. So 1 less than mod z less than 3, what does it represent? Look, mod z equals to 1 and mod z equals to 2. What do they represent? They represent circles. What am I drawing? Okay, let's little bit imperfect, but okay. So this is the origin. This is having radius 1 unit. This is having radius, let's say 3 unit, and this is having radius between 1 and 3. Right? This is the origin. This is having radius 1 unit. This is having radius, let's say 3 unit, and in between, let's say 2. So 1 less than mod z less than 3. So you have to expand this function in this region. You draw it in your way. I am drawing with my limited capacity of drawing. I am a very good artist, guys, as you can see. Okay, whatever it is, how bad it is, but I think you understood our point. So let us now expand this function. So f of z is equals to half, now 1 by, this is z plus 1, so we can write z times 1 into 1 plus z. Can you write it? You see, z is greater than 1. Here it means mod z is greater than 1, means 1 by mod z is less than 1. So that is why we have taken this one. 1 by z is less than 1 minus 1 upon 3 into 1 plus z by 3. Why do we take? Because you see mod z is less than 3, so mod z by 3 is less than 1. Option A. Option in it's not about option. We'll do for, this is not option, no? This one we will do for each case. This will give you one result, this will give you another result, this will give you another result, this will give you another result. So I am trying to make a difference between the results. Is it clear why you use half term? By simplifying this, 1 by z plus 1 minus 1 by z plus 3, if I simplify, this 2 comes in the numerator, so to settle that, half multiplied. This one you understood or not? Half 1 by z 1 plus 1 by z inverse minus 1/3 1 plus z by 3 inverse. So this is equals to half times 1 by z, 1 plus 1 by z inverse, so plus is there, so alternate sign will be there, 1 minus 1 by z plus 1 by z square minus 1 by z cube and so on, minus 1/3 1 minus z by 3 plus z by 3 whole square minus z by 3 whole cube plus so on. So if you just gather the coefficient, what you get? Look, half is multiplied, so 1 by 2z is there, so 1 upon 2z minus 1 upon 2z square plus 1 upon 2z cube minus 1 upon 2z to the power 4 plus, it will go on, then minus 1/3, and this minus this half is also multiplied, so minus 1/6 plus z upon 3 into 3 into 2 18 minus z square upon 54 will come plus z cube upon 162. Just we are simplifying the things. Now what you will get? You can keep the answer here also. So do you understand this one? Now let's go for the second condition. This is the expansion for this 1 less than mod z less than 3, and next one is mod z greater than 3. So what changes you can expect in this graph? look, the second region, it is mod z greater than 3. So mod z greater than 3 means we need to find a condition which is less than 1. So 3 by mod z is less than 1, है ना? So in the expansion we need to bring this 3 by mod z. Here for the first case we have got 1 by z, z by 3, both of them were less than 1. Here you have to find a condition 3 by mod z less than 1. Now as you can see, it is mod z greater than 3. So any mod z equals to 3, let's say it's looking like this. This is 3 unit. So this is mod z equals to 3. Now greater than 3 means what? The region beyond it. If I show you, so these are the region where you need to do the expansion. Mod z greater than 3, this outer region. Like any point here, is it clear now or not? Look, you will not make any difference in the calculation by looking at the picture, but you are getting to understand what is happening actually. So f of z is equals to half times 1 upon क्या था 1 upon z plus 1 minus 1 upon z plus 3. So we have to do something that we get in this form. So 3 by z is less than 1. So obviously this corresponds that 1 by mod z will always be less than 1, because if it's 3 times is less than 1, so it's 1 time will always be less than 1, है ना? So half times, if I take z common, so you get 1 plus 1 by z minus 1 by, here if you take z common, 1 plus 3 by z. So this is half 1 by z, 1 by 1 plus z inverse minus 1 by z, 1 plus 3 by z inverse. Clear? So this is 1 by 2z, 1 minus 1 by z plus 1 by z square minus 1 by z cube plus so on, minus 1 by 2z, 1 minus 3 by z plus 3 by z whole square minus 3 by z whole cube plus so on. So try to understand the difference. Here we required z by 3, which was less than 1. That is why we took 3 common. But here we require 3 by z. That is why we have taken z common. Are you able to get the difference? The difference is slight, but you have to be careful while writing this. So again we can just a little bit simplify, or if you just keep it like that, that will be okay. So as per the demand in the options, you can do a calculation. 1 by 2z minus 1 by 2z plus minus 1 by 2z square plus 3 by 2z square plus 1 by 2z cube minus 9 by 2z cube plus minus 1 by 2z to the power 4 plus 27 by 2z to the power 4 and so on. So ultimately this is 0. So you will get 1 by z square minus 4 by z cube plus 13 by z to the power 4 minus 50 by z to the power 5 and so on. So this is the required expression for this. The second one, can you do it for the third one? What is the third one? 0 less than z plus 1 less than 2, mod z plus 1. So mod of z plus 1, what does it represent? Let's go for the third case, okay? If anyone has any question, you can ask, okay? 0 less than mod of z plus 1 less than 2. So what you can conclude from here, as you can see, it is mod of z plus 1 greater than 0 and mod of z plus 1 less than 2. So mod of z plus 1 equals to 0 represents a circle which has a center z equals to minus 1, right? So let's do that. This is z equals to 0, z equals to minus 1, minus 2, minus 3 and so on. So z equals to minus 1, here the center lies, but the radius should be between 0 and 2. That is the meaning, na? The radius of this circle should lie between 0 and 2. So it is more than 0 unit, less than 2 unit. So if this is 0 plus 1 plus 2 and so on, so how will the graph look like? It should be more than 0 but less than 2. So if this is minus 1, 1, 2, so 1 से कम होगा, 2 से. Try to understand this very carefully, okay? Can you draw a circle like this? Okay, yes. Now as you can see, this is the circle whose radius is more than 0 unit but less than 2 unit. So any point z if you consider, so this is this point z and this is, let's say, z plus 1. So this is the circle, as you can see. What is this circle represent? Z plus 1, है ना? And if you had a circle here, this touching this point minus 3. This bigger dotted circle, this represents z plus 1 equals to 2. So this red one portion represents 0 less than mod z plus 1 less than 2. This one needs to be understood very clearly. Tell me if anyone has any doubt. Look, mod of z plus 1 less than 2, it means mod of z plus 1 by 2 less than 1. So f of z is equals to half, as usual 1 by 1 plus z minus 1 by z plus 3. This was there. So what we can do, we cannot do anything about this first term 1 by 1 plus z, but we can do something about the second term. We can write it as z plus 1 plus 2 half 1 by 1 plus z minus, you see, 1 by 2 1 plus z plus 1 by 2. So half times 1 plus z minus 1 by 4 times 1 plus z plus 1 by 2 inverse. Look, here we have z plus 1, so we can keep this first term. There is nothing to do, no need to do for the first term, but for the second term, as you can see, it is 1 plus z plus 1 by 2 less than 1, so we can write 1 plus, so positive sign is there, so alternate sign will be used, 1 minus z plus 1 by 2 plus z plus 1 by 2 whole square minus z plus 1 by 2 whole cube and so on. So you will ultimately get 1 upon 2 times 1 plus z minus 1 by 4 plus z plus 1 by 8 minus z plus 1 square by 16 and so on. Is it getting heavy, guys? Tell me, are you getting it difficult or you are understanding whatever I am telling you? This is not difficult actually, so easy to understand. If you have understood how to denote a circle in complex plane, let me reiterate it again. Mod of z equals to 1, this represents a circle which has a center at 0, radius 1 unit. Mod of z is equals to 2, center at the origin, radius has 2 unit. Mod of z is equals to 3, center at the origin, radius 3. Mod of z minus 1 equals to 1, circle which has a radius 1 but the center at z is equals to 1. Z plus 1 equals to 1, a unit circle having a center z equals to minus 1, है ना? Z plus 1 is equals to 3. This is a circle situated at z is equals to minus 1 having radius 3 units. This one is clear na? If this one is clear, I think everything will be all clear. Easy na? Okay, chalo. So last one, can you draw it by yourself? The condition can you draw? Mod z less than 1. So this is very easy. What does it represent? Can you tell me what does this mod z less than 1 represent? In words, if you represent, what does this mod z less than 1 represent? Which points? Circle at center origin, okay, that is, but mod z equals to 1 is the circle, but when I am talking about less than 1, what does it represent? When the circle mod z less than 1, mod z equals to 1 is this circle, mod z less than 1 means this inner point, right? Any point inside the circle. So this represents mod z equals to 1, and this regions represents mod z less than 1. Try to understand this fine difference. So mod z less than 1, it is already given, the condition is already given, so no need to struggle much here. So half, here z is less than 1, so 1 plus z inverse, here you can take this mod z is less than, so 3 you can take common, you know. If you take 3 common, what you get? 1 plus z by 3 inverse. So this is equals to half 1 minus z plus z square minus z cube and so on, minus 1/6 1 minus z by 3 plus z by 3 square minus z by 3 cube and so on. Now you can little bit simplify. Half will come from here, minus 1/6 will come from here, minus z by 2 will come from the first term, z by 18 will come from the, then z square terms, z square by 2 here, what is that? Z square by 9 into 6, 54, z cube minus z cube by 2, and here z cube by 162 and so on. So simplify a little bit more, 4 by 9z plus 13 by 27 z square minus 40 by 81 z cube and so on. So I think if you just do these 4 conditions separately, and previously what we have done in the last class, then I think any question from Laurents series you can tackle. Is it done? Let me give you another problem. All these 4 conditions you have already learned. This one you noted na? Ajay, Murli, Haran, Thamis, Deep. Harry, done? Okay. Now try to solve this special problem. Expand the following function in a Laurents series about the point z is equals to 0. The function is given to you, f of z is equals to 1 minus cos z by z cube. I think you can easily do it. Do it. Could you do this? You see, f of z is equals to 1 minus cos z by z cube. So 1 upon z cube, 1 minus cos z, you know how to expand. About z equals to 0 means the terms will come in the form of z, and for cos z you already know 1 minus z square by 2 factorial plus z to the power 4 by 4 factorial and so on. So 1 upon z cube, 1 minus 1 cancelled, minus minus plus, z square by 2 factorial minus z to the power 4 by 4 factorial plus z to the power 6 by 6 factorial minus dot dot dot. So this is 1 upon 2 factorial times 1 upon z minus 1 upon 4 factorial times z plus 1 upon 6 factorial times z cube minus so on. Okay, so this is the answer. We can write it in a compact form, in the form of a summation. Let's say sum over. So alternate sign have been used, so we can use -1 to the power y to the power n, z, then z cube. Here it is, you can see the power of z is -1, then it becomes +1, then it becomes 3, then it becomes 5. So 2 unit difference, है ना? So for 2 unit difference, when at z to the power 2n minus 5 if we write, and let's say n is equals to 2 to infinity. The first term is plus z to the power 2 into 2 minus 5. So z to the power -1 divided by 2 factorial means here you have to write 2n minus 2 factorial. Now check whether it is satisfying or not. If you put n is equals to 2, so 4 minus 2 factorial. Okay, let's take the second term, n equals to 3 you put, so negative 2 into 3 minus 5, so z divided by 2 into 3 minus 2, 6 minus 2, 4 factorial, and it will be satisfied. Clear this one? Let us now talk about separately singularity of a complex function. You have already done this one, you already understand what is singular point. Let us do it in little more detail. Let's know more about this singularity of complex functions. So give this heading. First of all, we'll start with what to understand by singular points of a function. Singular points of a function. Can anyone tell me what do you understand by singular point of a function? You can ignore the final step. Final step we have just written like in the form of a summation, just nothing else. By looking at the terms, you can keep your answer up to this. By looking at the terms, we have tried to formulate a summation. Okay, no? So if you write the summation, you start with n equals to 2 to infinity, then you get this one. Or if it is appearing to be difficult, you can just ignore this. The way we write, let's say 1 plus x square by 2 factorial plus x cube by 3 factorial and so on, we write it in the form of summation for a compact form, x to the power n by n factorial, n equals to 0 to infinity. So similar kind of summation we have tried to formulate here. Function is not analytic at that point. Yes, those are the singular points. So the point at which the function ceases to be analytic. The point at which the function ceases to be analytic are said to be the singular points cease बोलना पड़ेगा, cease to be analytic, to be singular points of the function. Simple example, if you take f of z 1 by z plus 3 has a singularity at z is equals to, tell me quickly, minus 3. Now, if I classify these singularities, how many different types exist? So, primarily it is classified into two categories: isolated singularity and non-isolated singularity. Isolated singularity, so as it is clear from the name, isolated singularity means there is no other singularity in the neighborhood of that singularity. This is isolated. Another type is non-isolated singularity. So, non-isolated singularity means in the neighborhood of the singular point there will be other singular points. Yes. Now, this isolated singularity had got several types. Isolated singularities will have several types. They include removable singularity, then non-essential singularity, non-essential singularity, which are also called poles, and third one is essential singularity. Okay, and non-isolated is non-isolated one type. So, we have to know about this singularity. First of all, let us talk about this isolated singularity. Isolated, this can be an isolated singularity, right? Because at beside z equals to minus 3 there is no other singularity. Let me give you one example. Just note it down. So, we will start with isolated singularity. The definition is clear. For isolated singularity, there will be singularity at some point and there will be no other singularity in the neighborhood of that point. Number 1, isolated singularity. These are very easy concept, you can easily understand. A point z is equals to z0 is said to be an isolated singularity if the first criteria is clear, f of z is not analytic, at z equals to z0, and the second criteria is fz is analytic in the neighborhood of z is equals to z0, means z equals to z0 is the only singular point. That is, there exists a neighborhood of z is equals to z0 containing no other singularity. You can imagine it in this way, that we have a wide place, okay? And at only small place a borehole has been made, and there is no borehole other than that. The examples are very trivial. Let us say, if you consider f of z, this is equals to 1 by z, so it is analytic everywhere except at z equals to 0. This is analytic everywhere at except is analytic everywhere except at z is equals to 0, and therefore z is equals to 0 is an isolated singularity. Another example that will make the scene more clearer. Let's say it is z plus 1 divided by z minus 1, z minus 2, z minus 3. So it has singular points. So 3 isolated singularities at z is equals to 1, 2 and 3. So as you can see, this is 0, this is 1, 2, 3. So we have the singularity here, 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 and as you can see, in the neighborhood of 1 there is no other singularity until you reach to 2. In the neighborhood of 2 there is no singularities, like 1.5 is not there, 1.01 is not there, 1.02 is not there, only 1, 2. So they are isolated. 3, they are isolated singularities. Clear? Now non-isolated singularity. So similar kind of definition will be there. Let's do it on the next page. Okay. you don't have the option to copy paste, so you will write so non-isolated. So at point z equals to z0, at point, a point, what we write, a point z equals to z0 is said to be an non-isolated. So n will be a, said to be a non-isolated singularity if fz is not analytic at z equals to z0 and there exists a neighborhood of z equals to z0 containing other singularities. Okay, so we have to write it. There exists a neighborhood of z is equals to z0 containing other singularities of f of z. What do I mean? If I take an example, then it will be very much clear to you. Let us say we have a function f of z is equals to 1 upon sin pi by z. So generally in your problems you will be dealing with isolated singularity. Non-isolated singularity is not given generally. So how to check the singular point? You make the denominator equals to 0, na? More than one singular point, yes, more than one. We will check this one. For this case, you see, what is the condition of singularity? Condition of singularity. So you know the meaning of isolated and non-isolated, right? Isolated means you are alone. Non-isolated means in addition to you there will be someone else also. Condition of singularity, you set the denominator equals to 0, right? So sin pi z equals to 0, so that is equals to sin n pi, and we can write pi by z is equals to n pi, and hence z is equals to 1 upon n. So if you put n equals to 0, 1, 2, 3 up to infinity, you will get different values of n, different values of z. For all values of z, the sin pi by z will be 0 and f of z will be not analytic. So if I say that the point z is equals to 0 by taking n equals to infinity, z equals to 0 you get, so sin 0, that makes f of z not analytic. So the point z equals to 0 corresponding to n tends to infinity will be surrounded by infinite number of other singularities. Surrounded by infinitely many singular points of f of z. Thus z is equals to 0 is a non-isolated singular point. of f of z. So as you can see, if we draw try to understand this. This is y, this is x. This is your z is equals to 0, and by taking n equals to infinity. So if you take z is equals to 1, sorry, n equals to 1, z equals to 1, this is a singular point. If you take n equals to 2, so z equals to half, so this is also a singular point, this is a singular point, this is a singular point. N equals to 3 you take, you get 1/3, so you get another singular point. N equals to 4, closer to 0, you get another singular point. So as you put higher values of n, you will get singular point. All of these are singular points. So infinitely many singular point you are getting in the neighborhood of z equals to 0. So z equals to 0 is not an isolated singularity, it is a non-isolated singularity. Is it clear or not? Tell me. Now mainly in your problem this non-isolated singularity does not come, but for your conceptual purpose we have just provided non-isolated. Now if we talk about isolated singularity, there are various types, as I mentioned, removable, non-essential and essential. So let us talk about that. Firstly, removable singularity. As the name suggests, the singularity can be removed. Look, give the heading types of isolated singularity. To understand these types of isolated singularity, now you will introduce Laurents series here. If f of z is an isolated singularity point, f of z has an isolated singular point, let us say at z is equals to a. Then we can expand f of z about z is equals to a into Laurents series. How do you expand in Laurents series? F of z is equals to, you write n is equals to 0 to infinity an z minus a whole to the power n plus n equals to 1 to infinity bn by z minus a whole to the power n, right? This part is known as the principal part of the expansion. This part has got a name, principal part of the expansion, है ना? And this one you can further expand the way you did a0, a1, a2 and so on, plus b1 by z minus a, b2 z minus a whole square, b3 z minus a whole cube, and so on. No issue in this. So based on this, how many terms survives, how many terms vanishes, based on this we define these three types of isolated singularity. Let's write it in the denominator. So let's write it here so that it becomes clear to you. It's a height of laziness. Now based on this, the three types of singularities you will get. The three types of singularities are as follows. Number one, the removable singularity. What is removable singularity? If the second part, principal part, becomes 0, है ना? If the principal part of the expansion Laurents series expansion of f of z about z is equals to a contains no terms है ना, that is bn is equals to 0 for all n, then we can say that z is equals to a is a removable singular point. Then f of z has a removable singularity at z is equals to a. This is quite obvious. You see, this term gives you, like if you put n equals to 1, it gives you 1 by z minus a, then b2 by z minus a whole square, b3 by z minus a whole cube. So removable means this singularity will not be there, है ना, only terms in the numerator will be there, z minus a, z minus a whole square, z minus a whole cube, and so on. So this is the removable singularity. I think it is very much clear. So for this removable singularity, the Laurents series expansion will become like this. In this case, the Laurents series expansion become f of z is equals to n is equals to 0 to infinity a n z minus a whole to the power n. All the bm terms are vanishing. Let's give an example, then you will understand it better. For an example, if you have a function f of z is equals to sine z by z. So as you can see, it has a singular point at z equals to 0. but if you multiply with z, this singular point is vanished, or as you can see it is 1 by z times sin z is z minus z cube by 3 factorial z to the power 5 by 5 factorial and so on. So as you can see it is 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial and so on. So is there any negative term? Look, if the value of n, if you consider this, it is like b1 z minus a to the power minus 1, right? If you take it to the numerator, z minus a to the power minus 2, है ना? So there is no negative term, you can see. So we can say that bn are all 0 for this series, since there is no negative term in the Laurents series. Expansion of f of z about, here z is equals to 0 was the singular point, right? Hence z is equals to 0 is a removable singularity of f of z. Clear? Now for pole, you know, if you remember, you have done it already unknowingly, maybe knowingly or unknowingly, 1 by z minus 1, let's say. So it is a pole of order 1. So pole lies at z equals to 1, है ना? So actually it is nothing but z minus 1 to the power minus 1, right? This is the first term of the principal part. Removable singularity we understood. Let's go for non-essential singularity. Also known as pole. It means, look, not all the terms of the principal part are 0, few terms survives, but not infinitely many number of terms survives. Understanding? You see, the principal part goes from n equals to 1 to infinity. So for removable singularity, as I told you, that this whole part is 0. Now it may happen that only the first 3-4 terms survive, let's say n equals to 1, 2, 3, 4, up to this survives, and the remaining terms 4 to infinity, those are 0. So in that case, that is called non-essential singularity or pole. So if I give you the definition, if the principal part of the Laurents series expansion of f of z about z is equals to a contains finite number of terms. It may be 2 terms, it may be 1 term, it may be 3 terms, it may be 4 terms. So let's say m number of terms is finite. So Bn will become 0 for all n which are greater than m, है ना. So let's say 4 terms survives. So b1, b2, b3, b4, those will be non-zero. Then after, let's say b5, b6 and up to infinity, that will be 0. Then we can say that f of z has a non-essential singularity or pole of order m. So if 2 terms survives, that will be pole of order 2. If 3 terms survives, pole of order 3. If 1 term survives, pole of order 1 or single pole. So pole of order m at z is equals to a. And to note, a pole of order 1 is known as simple pole. A pole of order 1 is known as a simple pole. So now what will be the expansion? What will be the form of the expansion? So thus, if z is equals to a is a pole of order, let's say m, of the function f of z, then f of z can be written in the Laurents series expansion as, the theory is getting too much, but I think that is necessary. F of z is equals to, you see, the first part will remain as it is, n equals to 0 to infinity n z minus z0 or z minus a to the power n plus n is equals to 1 to infinity. We will not take infinity because up to, it is a pole of order m. So up to m number of term it will survive. So we can write bn z minus a by n was there, so to the power minus n you can write, taking to the numerator. For an example, if I take an example, then it will be very much clear to you. Let's say we have a function like f of z, z by z minus 1, z plus 2 whole square. So it has a simple pole at z is equals to 1 and a pole of order 2 at which point? Tell me. Pole of order 2 at which point? Harry, Murli, Ajay, Deep, Thamis. At which point the pole of order 2 will exist? Minus 2. So this is your non-essential. So from this, can you tell me what is essential? For essential, what we will have? What should be the condition for essential singularity? Look, for removable, principal part contains no terms. For non-essential, principal part contains finite number of terms, maybe 2, 3, 4 or something like that. So, what will be for essential singularity? How many terms it should contain? Batao guys, if the principal part of the Laurents series expansion contains how many terms? B and n terms exist. N term is what is the value of n? Here also n term exists. What n equals to 1 to infinity was there. So for essential, how many terms should exist? If the principal part of the Laurents series expansion of f of z about z equals to a contain, what may be the possibility? Infinite terms, yes, contains infinite number of terms. That is Bn not equals to 0 for infinitely many values of n. Then f of z has an essential singularity at z is equals to a. So page is running out. So let's take the example here. A very specific example is there. These are like exceptional cases. So if you consider a term like f of z is equals to e to the power 1 by z, 1 minus infinity क्यों होगा? Infinite. One term you are excluding y. So you see, what is the meaning of containing infinite terms? Means this will continue 1 by z, 1 by z is, or let's say if z equals to 0, if you consider 1 by z, 1 by z square, 1 by z cube, 1 by z to the power 4, z to the power 5, 1 by z to the power 7 and up to infinity. So if you expand this e to the power 1 by z, so this is 1 plus 1 by z plus 1 by z square 2 factorial plus 1 by z cube 3 factorial plus dot 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 up to infinity. So you can see it containing infinite number of terms which has denominator z. So z to the power 1. So it is like putting n equals to 1, n equals to 2, n equals to 3, n equals to 4. It will go up to infinity. So it is containing infinite number of terms in the principal series. So we can say for this function f of z, what you can conclude from here for this example? That is, we can say f of z has an essential singularity at z is equals to where? Can you tell me? Yes, 1 to infinity. Yes, f of z for this function f of z equals to e to the power 1 by z. Can you tell me where this function has an essential singularity, at z equals to where? At which point of z f of z contains essential singularity z equals to 0. Very good. Because as you can see, it is like 1 by z minus 0, 1 by z minus 0 whole square, z minus 0 whole cube, and so on. So all the concept clear now? Singularity, isolated, non-isolated. In isolated we have removable, non-essential, and essential. One problem, let's do. Think little bit and answer. Determine the nature of singularity of the functions z minus 3 sine 1 by z plus 2. Is it a non-isolated singular point? Acha. Determine the nature of singularity of the function z minus 3. Okay. First of all, you calculate singular points. Singular points, what are the singular points? You tell me two things. What is the singular point and what is the nature? So I am giving you the options for the nature of singularity. So you have to tell me both. Here the singular point option is not given, only nature of singularity is given. So what is the singular point for this case? क्या बोल रहे हो? आइसोलेटेड एसेंशियल सिंगुलर पॉइंट. Singular point, what is the singular point then? What is the singular point of this function? Ajay, Deep, Hari, Murli, Thamis. Z equals to minus 2. Very good. Z is equals to minus 2. It is a singular point. Pi by z plus 2 कहाँ से आ गया? It is in the numerator, okay, not in the denominator that you will make it to sin n pi के साथ equate करोगे. It is not in the denominator that you will make this sin n pi. It is in the numerator, na? So you can expand it. So z minus 3 times sin 1 upon z plus 2. If it were in the denominator, then we could have done that, but for this we can expand. We know the sine series x minus x cube by 3, x cube by 3 factorial, sorry, plus x to the power 5 by 5 factorial. So how many terms it contains? In the denominator, the powers, it will extend up to infinity. So this is an essential singular point, है ना? And as you can see, z plus 2 cube, so z is equals to minus 2 is a singular point, and this is isolated. There is no other singularity beside z equals to minus 2, है ना? So that is why this is an isolated, and as there are infinite number of terms, that is why it is essential. Just revise this concept 1 or 2 times at home, then I think this thing will be clear very much. Not difficult. Okay, you just need to revise. So I hope you have understood this singular points and all. From the next day we will go for residue and contour integration. Okay, we will talk about methods of finding residues, then how to solve integration by complex analysis method and all those things. So we are stopping here today, guys. If anyone has any question, you can let me know, and all of you like the video. Okay, thank you very much for joining this session. We will meet again tomorrow at 7:30 AM. Bye bye. Take care, guys. Have a great day. This was a quite long session, right? 2 hours plus. Chalo. Bye bye.